Every morning, Sam watches the perfectly poured lattes go out the door and wonders, how much milk should I order for tomorrow? Order too much and it spoils. Order too little and he turns away paying customers. Sam's true goal is to pinpoint tomorrow's total sales. In the language of math, this target number is known as the response, the final outcome he's trying to reach. These sales aren't random. They're driven by specific patterns from the past. We call the factors that influence the total, like the weather or the day of the week, the features. Temperature exists on a sliding scale. When the mercury dips toward freezing, hot coffee sales rise. Other factors belong to categories, like weekends versus weekdays. A Saturday rush follows a different pattern than a Tuesday, which Sam must account for. When we combine these pieces, we get a foundational equation. Sales equals the mathematical relationship between the environment plus a little bit of random luck. That random luck represents the error we can never fully remove. If a customer trips and spills their latte on the way out, they will come back in for a second cup. No calculation can account for a clumsy moment or a sudden mood shift. This process is the core of statistical learning, looking at the relationship between what we already know and what we want to happen, while leaving a little room for the unavoidable chaos of the real world. To find that relationship for tomorrow, Sam has to look backward. He needs to see how his sales actually behaved over the last few months. Looking at figure 1.1, a simple scatter plot tracks input temperature against coffee sold. When Sam looks at figure 1.2, tracking thousands of days, the dense gray cloud clearly shows that as temperature changes, sales respond. But seeing the pattern is only the first step. Sam has to decide what he actually wants this data to do for his business. If he simply wants an automated tool that spits out a milk order number every morning, he's focused on prediction. Here, the accuracy of the number is everything, and the internal logic of the math matters less than the result. On the other hand, if he wants to understand exactly how a heat wave changes customer behavior so he can design a new menu, he's looking for inference. He needs to understand the why behind the numbers. How we use our data, whether we want an automated answer or a deep understanding, determines how complex our mathematical model needs to be. To make a prediction, Sam needs to draw a line through his historical data dots. He could choose a perfectly straight line cutting through the center. This is a parametric approach, assuming the relationship follows a simple set form. This rigid line misses natural curves in the data, creating high bias. Alternatively, he could use a model that squiggles and bends to touch every single dot perfectly. This non-parametric approach just follows the data wherever it goes. This is a trap. By perfectly following every historical dot, the model has memorized the random noise and the one-off accidents of the past. When Sam tries to use this jagged line to predict a new day, it will likely miss the mark entirely. The goal is generalization. We want to capture the true signal of the trend, while ignoring the random static that won't happen the same way twice. The best model is the one that curves just enough to catch the real trend, but stays stiff enough to ignore the daily anomalies. To prove his model works, Sam tests it against days he hasn't looked at yet, what we call test data. If his line can accurately predict sales for a day it has never seen, he knows he's found the right balance. Because Sam is trying to predict a specific quantity, like gallons of milk or a number of cups, he is solving a regression problem. But if he were sorting things into categories, like a doctor deciding if a treatment will be effective or not effective, he would be dealing with classification. Instead of a number, he's looking for the right bucket. Whether you're managing a coffee shop, forecasting the global weather, or analyzing a medical trial, the underlying logic is the same. We take the patterns we've seen, account for the fact that the world is a bit messy, and draw the most logical line possible toward the future.